Take a deep, slow breath in and let your body settle completely into the comforting, heavy weight of the space around you. Allow your mind to drift far beyond the boundaries of our solar system, traveling safely to a place of profound, radiant warmth and hypnotic geological rhythms. We are journeying exactly 41 light-years away from Earth, looking toward the northern sky into the constellation of Cancer, to arrive at a mesmerizing world known to astronomers as 55 Cancri A. What is truly fascinating about this exoplanet is that it orbits its host star so closely that its entire surface is not made of rock or water, but consists of a vast, globally continuous, gently rolling ocean of liquid lava. Here's something most people don't know. This planet, officially named Janssen, was first discovered in the year 2004. It was found using a technique called the radial velocity method. In this method, astronomers observe the host star, a yellow dwarf named Copernicus, or 55 Cancri A, and look for a delicate rhythmic wobble in its motion. This wobble is caused by the gravitational pull of the planet tugging on the star as it circles it. Imagine that gentle swaying motion for a moment. The star, slightly smaller and just a bit cooler than our own sun, moves back and forth in a steady cosmic pendulum swing, a celestial lullaby that has been repeating for billions of years in the quiet vacuum of space. As we draw closer to 55 Cancri E, the first thing you might notice as a peaceful observer is the profound sense of scale and density. This world belongs to a class of planets known as super-Earths. It has a radius approximately 1.95 times that of our own planet, meaning it is nearly twice as wide. But more impressively, it possesses a mass roughly 8 times greater than Earth's. Because of this incredibly dense concentration of matter, the gravity here is remarkably strong. In your mind's eye, you can experience this not as a burden, but as a deeply soothing, grounding force. It feels like a massive cosmic weighted blanket, pulling all the tension down and away from your muscles, anchoring you safely as you observe the immense geological wonders below. The mechanics of this planet's orbit are equally extraordinary. 55 Cancri E sits at a distance of only 1.5 million miles from its star, Copernicus. To put that into perspective, Earth rests comfortably at 93 million miles from the Sun. Because Janssen is tucked in so close, it completes an entire orbit in a mere 18 hours. An entire year on this planet, a full journey around its sun, passes in less than a single Earth day. Time here moves in a rapid, continuous loop, a smooth and never-ending cycle that creates a hypnotic, steady rhythm, spinning through the dark velvet of space with perfectly predictable grace. Because of this extreme proximity to the star, 55 Cancri E experiences a phenomenon known as tidal locking. Just as we only ever see one side of our moon from Earth, this planet keeps one hemisphere permanently facing its sun, while the other side is locked in eternal night. On the dayside, the star hangs motionless in the sky, a massive, brilliant orb radiating a constant, unwavering stream of thermal energy. You are completely insulated and protected as an observer, allowing you to simply feel the profound, penetrating warmth of this environment. The temperature on this sun-facing hemisphere reaches an astounding 4,300 degrees Fahrenheit, or about 2,400 degrees Celsius. At this immense temperature, solid stone simply cannot exist. The heat melts the planet's rocky crust, creating a deep, glowing ocean of molten silicates. Look down upon the surface. This is not a chaotic place of violent eruptions, but rather a slow, viscous sea of liquid rock, Because the magma is composed of heavy silicate minerals, it does not splash or crash like oceanic water on Earth. Instead, it moves with a thick, heavy fluidity. Great sweeping currents of gold, orange, and blinding white slowly swell and fold over one another. Listen closely with your imagination. The sound of this ocean is a low, continuous, subsonic rumble. It is the deep, resonant hum of billions of tons of liquefied stone shifting under extreme gravity, vibrating at a frequency so low and steady that it seems to massage the mind. For many years, the exact nature of the space directly above this lava ocean remained a mystery. But recently, observations from the James Webb Space Telescope have revealed another deeply fascinating fact about 55 Cancri e. By capturing the incredibly faint infrared light emitted by the planet, scientists have found strong evidence that this world possesses a thick, dynamic atmosphere. The data suggests this heavy blanket of gas is rich in either carbon dioxide or carbon monoxide. Imagine looking up from the glowing oceans of magma. The sky is not the transparent black of a vacuum, but a dense, hazy expanse, shimmering with the intense heat. This thick atmosphere filters the starlight into a continuous, warm amber glow, softening the harshness of the star into a rich golden hue that wraps around the entire dayside. What is particularly elegant about this atmosphere is its role in the planet's global climate system. In a vacuum, the dark side of a tidally locked planet would be unimaginably cold. However, the thick carbon-rich gases on 55 Cancri e act as an incredibly efficient thermal conveyor belt. The atmosphere absorbs the immense heat from the 4,300-degree dayside and physically carries it across the terminator line, the twilight boundary dividing day and night. You can almost sense these massive, slow-moving atmospheric currents, rivers of superheated gas flowing smoothly through the sky, carrying radiant thermal energy to the dark side of the world. It is a perfect, continuous system of natural redistribution, a planetary balancing act playing out in slow motion. Because of this efficient heat transfer, the night side of 55 Cancri e is far from freezing. Even in the total absence of direct starlight, the temperature on the dark hemisphere hovers around 2,000 degrees Fahrenheit, or 1,100 degrees Celsius. Let your perspective drift across the terminator line into the eternal night. Here, the sensory experience shifts. The blinding golds and whites of the dayside magma transition slowly. The molten silicates begin to cool ever so slightly in the darkness, shifting in color to a deep, soothing cherry red. At 2,000 degrees, the lava becomes even more viscous, perhaps developing temporary thin crusts of darkened, solidifying rock that drift across the glowing Red Sea like massive puzzle pieces. The contrast between the pitch-black sky and the deep dark crimson of the cooling magma ocean creates a beautifully serene, dimly lit landscape. The heat here is slightly less intense, felt as a gentle ambient warmth radiating upward from the glowing seams in the darkening rock. There is a fascinating history to how we have understood this world. When 55 Cancri e was first studied closely, some early models of its mass and density suggested it might be extremely rich in carbon. Under the immense pressure and heat of the planet's interior, scientists theorized that much of the planet's mantle could be compressed into solid diamond. For years, it was famously referred to in the public imagination as the Diamond Planet. While more recent data points to the rocky, silicate-rich magma ocean we are observing now, in the sheer pressure deep within its core remains a physical marvel. The weight of 8 Earths compressing inward creates a dense, highly structured interior, a silent, locked heart of heavy elements supporting the vast fluid oceans above. You can almost feel that incredible internal stability, a strong, unyielding core that anchors the entire glowing world. Every aspect of 55 Cancri E offers a masterclass in the grand, slow-moving physics of the universe. Consider the interplay of light and shadow when the planet passes directly between its star and our telescopes on Earth. This event, known as a transit, occurs every 18 hours. During a transit, the planet blocks a tiny fraction of the star's light. As the starlight filters through the edges of the planet's carbon-rich atmosphere, it carries the chemical signature of the air across 41 light-years of empty space. It is a quiet, continuous broadcasting of its own existence, an interstellar whisper that our most sensitive instruments have finally learned to hear. As you safely observe this world, allow the sensory details to wash over you. Feel the steady, heavy pull of the super-Earth's gravity, easing away all lightness and restless energy from your frame. Bask in the continuous, unwavering thermal embrace of the dayside, a 4,300-degree heat that you experience only as a profoundly relaxing deep-tissue warmth. Watch the thick golden silicates welling up from the planet's interior, heavy waves of liquid light folding over one another in a slow, hypnotic rhythm. Listen to the deep, resonant, low-frequency hum of a world entirely covered in liquid rock. A soothing planetary vibration that has remained uninterrupted since the dawn of this star system. Here, there are no sudden changes. There are no unpredictable storms of water or ice. There is only the steady 18-hour orbit, the constant glowing heat, and the slow, majestic currents of a magma ocean moving gracefully under a hazy amber sky. The environment is absolute in its consistency, a perfect enduring system of gravity, heat, and fluid stone. Allow yourself to be entirely captivated by the grand, sweeping scale of this molten world, sinking deeper into the comforting warmth and the heavy, peaceful rhythms of Exoplanet 55 Cancri E. To fully appreciate the quiet majesty of this glowing world, look upward for a moment, away from the molten surface of Janssen, and observe the ancient host star it orbits. Copernicus is much older than our own sun. Astronomers estimate its age to be between 7.4 and 8.7 billion years old. It has been burning steadily through the cosmos for nearly twice as long as our solar system has existed. What makes this particular yellow dwarf so special in the history of astronomy is its brilliance as seen from our own world. Copernicus shines with an apparent magnitude of 5.95. This means that on a clear, dark night on Earth, far from city lights, human eyes can see this exact star without the aid of a telescope. Janssen holds the profound distinction of being the first super-Earth ever discovered orbiting a naked-eye star. Trace back to the origins of our understanding, to a time long before we knew of the lava oceans below. The existence of Exoplanet 55 Cancri E was first announced on August 30th, 2004. We, a dedicated team of researchers at the University of Texas, including astronomer Barbara MacArthur, detected the incredibly faint gravitational signature of this world, hidden within the star's light. It was the fourth planet identified in this busy solar system, which is why it bears the letter E, following the discoveries of planets B, C, and D. For years, the true nature of this world was veiled in mathematical misunderstanding. Early models, relying on the limited data of the early 2000s, calculated the planet's orbit to take 2.8 days. It wasn't until the year 2011 that two researchers, Rebecca Dawson and Daniel Fabricki, meticulously reanalyzed the archival data. They discovered the subtle anomalies in the readings and uncovered the planet's true blistering 18-hour orbital period. Think of an antique celestial clock where the internal gears were originally misidentified by its caretakers. Once the correct mathematical cog was slotted into place, the rapid, breathless speed of the planet's year suddenly made perfect mechanical sense. Later that same year, a Canadian space telescope known as MOST, short for microvariability and oscillations of stars, managed to catch Janssen in the act of transiting its star. This was a monumental historical achievement, physically confirming the planet's tight, rapid path. To honor this growing body of knowledge, the International Astronomical Union officially gave the planet its name in 2015. They called it Janssen, a tribute to Zacharias Janssen, the 16th century Dutch spectacle maker, often credited with inventing the first optical telescope. The star was formally named Copernicus, honoring the Renaissance astronomer who first placed the sun at the center of our universe. Centuries of human curiosity culminated in the naming of this distant, molten globe. Deep within the scientific archives of 2016 lies another massive breakthrough in how we map the unknown. Using the Spitzer Space Telescope, scientists managed to record the infrared emissions of Janssen as it orbited, creating a phase curve. This resulted in the very first thermal map ever created of a super-Earth. By charting the heat distribution across the planet's surface, they found something deeply counterintuitive. Logic dictates that the hottest point on a tidally locked planet should be the substellar point, the exact geographical spot directly beneath the star, where the radiation hits at a perfect, impunishing 90-degree angle. Instead, the thermal map revealed that the absolute hottest point on Janssen is shifted 41 degrees to the east of the substellar point. This dramatic shift is a physical fingerprint of the planet's thick, heavy atmosphere. To visualize this process, picture a massive invisible river of superheated gas rushing continuously eastward. The atmosphere physically absorbs the stellar radiation and sweeps it away before it can peak. The thermal energy is carried like a heavy plume of sediment in a fast-flowing current. By the time the magma and atmospheric gases reach their maximum temperature, the powerful eastward winds have already blown them 41 degrees away from the star's direct glare. Consider the immense chemical reality required to create such powerful atmospheric currents. The surface pressure on Janssen is extraordinary, estimated by some models to be up to 100 times greater than Earth's atmospheric pressure at sea level. At 100 atmospheres of pressure, gas behaves almost like a dense, heavy fluid, pressing down on the molten ocean with suffocating weight. This thick envelope is not made of oxygen or nitrogen, but is heavily saturated with vaporized rock. The extreme 4,300 degree Fahrenheit temperatures on the dayside are more than sufficient to boil solid minerals. Elements such as silicon dioxide and sodium evaporate directly from the glowing ocean, rising as a dense, mineral-rich fog into the amber sky. As these silica-laden winds cross the terminator line, drifting away from the eternal day and into the cooler 2,000-degree temperatures of the night side, a spectacular meteorological transformation occurs. The vaporized silicon dioxide rapidly loses its heat. It transitions from a gas back into a liquid state, generating a weather phenomenon known as mineral rain. Notice the deep, heavy silence of this alien weather system. Droplets of molten glass and cooling liquid rock condense in the dark clouds and fall continuously through the thick air. They splash smoothly into the dense, red-glowing lava sea below, creating a gentle, heavy patter of liquid stone returning to the ocean. Scientists believe the composition of this expansive magma ocean is primarily made of plagioclase, feldspar, and pyroxene. These are common volcanic silicates, the exact same minerals found churning deep within Earth's own mantle, beneath our tectonic plates. Watching this ocean is like peering into the primordial past of our own world, a time when the Earth's crust was still a fluid, shifting sea of glowing heat. At this very moment, another immense physical force dictates the rhythm of these waves. The surface gravity on Janssen is measured at 2.1 times the gravity of Earth. Everything here is subjected to a profound downward pressure. An object weighing 100 pounds on our home planet would weigh 210 pounds here. This intense gravitational pull acts as a natural dampener on the landscape. It flattens the rolling waves of the magma ocean, preventing tall crests from forming. Instead of chaotic, crashing surf, the liquid stone is forced into broad, shallow, heavy ripples that glide slowly across the surface, weighed down by the massive density of the planetary core. Even the wider neighborhood of this star system provides an incredible sense of scale and ancient stability. Copernicus is not alone in the dark. It is part of a binary star system. If you were to look out from the night side of Janssen, past the falling mineral rain, you might spot a distant, dim red glow. This is 55 Cancri b, a smaller red dwarf companion star. It sits incredibly far away, orbiting at a distance of over 1,000 astronomical units, more than 1,000 times the distance between Earth and our Sun. It takes tens of thousands of years for this red dwarf to complete a single orbit around Copernicus, a slow, majestic cosmic dance that has continued undisturbed for over 7 billion years. Knowing the history of our observations adds a profound layer of depth to the glowing red oceans below. What was once just a tiny rhythmic wobble detected by a telescope in Texas has slowly resolved into a vividly detailed world. We have mapped its heat, measured its immense gravity, and deduced the composition of its glassy mineral rains. The heavy pressurized air, the flattened glowing waves of feldspar and pyroxene, and the eastward rushing winds all operate in a perfect, continuous cycle. The geology of Janssen requires no intervention. It is a self-sustaining engine of thermal dynamics and fluid mechanics, echoing across 41 light-years of silent space. Observe the slow, heavy movement of the molten rock, resting comfortably in the knowledge that this ancient glowing system will continue its warm, steady orbit long into the deep future. Look closely at the physical texture of this glowing ocean, and you will notice a rhythm that feels surprisingly familiar, despite the extreme alien environment. To truly understand how this molten sea moves, we must look at the mechanics holding it together. The escape velocity of exoplanet 55 Cancri e, the exact speed required for any object or gas to break free from its gravitational grip, is approximately 23 kilometers per second. On our home planet, escape velocity is only 11.2 kilometers per second. To picture this incredible force, imagine the speed of a high-powered rifle bullet, which travels at roughly 1 kilometer per second. The gravity here is so relentless that a gas molecule would need to travel more than 20 times the speed of that bullet just to slip away into space. Because of this inescapable downward pull, the atmosphere is structured differently than anything we experience on Earth. Scientists measure atmospheres using a concept called scale height, which is the vertical distance over which atmospheric pressure decreases by a specific factor. On Earth, our atmospheric scale height is about 8.5 kilometers, giving us a tall, breathable sky. On Janssen, the immense gravity violently compresses the scale height. The heavy carbon gases do not stretch tall. They are squashed tight against the molten ocean. It is exactly like taking a thick, fluffy down pillow and compressing it tightly until it resembles a heavy, dense pad of felt. This creates an incredibly dense envelope of air that hugs the surface, wrapping the world in a tight thermal embrace. Deep within the planet's overall structure, Shatsan, we find a density that dictates the very shape of its waves. By dividing the planet's mass of 8 Earths by its volume, astronomers calculate its overall density to be about 5.95 grams per cubic centimeter. This means the entire globe is denser than a solid anvil of cast iron. Consequently, the magma rolling across the surface does not behave like liquid water. Due to the mineral composition and the crushing gravity, the viscosity of the liquid stone is remarkably high. When you pour cold honey from a jar, or when you knead a dense, heavy bowl of warm bread dough, you witness this exact type of slow, sluggish resistance. The waves on this world do not crest and break. They heave. They roll with a delayed, syrupy momentum, a beautiful slow-motion ballet of glowing amber fluid. Consider what is happening beneath the surface of this dense ocean. The core of the planet is thousands of degrees hotter than the surface. This immense internal heat is continuously fueled by a process called tidal heating. As the planet orbits, the massive gravitational pull of the nearby star slightly stretches and flexes the planet's rocky interior, creating internal friction. This friction generates a constant soothing heat from the inside out. Because of this internal warmth, massive convection currents form within the liquid mantle. Picture a large pot of thick oatmeal simmering gently on a warm kitchen stove. As the material at the bottom heats up, it expands, becomes lighter, and slowly rises to the surface. Once it reaches the top, it releases its heat, cools slightly, and sinks back down in a continuous, rolling cycle. On 55 Cancri E, these convection cells operate on a planetary scale. Columns of superheated magma, hundreds of miles wide, steadily well up from the deep interior, breaking the surface in massive, glowing upwellings that bring fresh thermal energy to the dayside ocean. Notice how, as these massive upwellings reach the top, a quiet, unseen exchange takes place. The rising magma carries dissolved volatile gases, primarily carbon monoxide and carbon dioxide, trapped deep within the planet's interior. As the liquid stone breaches the surface, the pressure shifts, allowing these gases to gently release into the heavy atmosphere. The physics of this outgassing are perfectly mirrored in your own kitchen when you twist the cap off a bottle of carbonated sparkling water. The sudden change in pressure allows the dissolved carbon dioxide to separate from the liquid, rising as tiny bubbles. Across the vast magma oceans of Janssen, this exact carbonated release happens continuously, a quiet, steady exhalation of planetary breath feeding the thick, hazy sky. If we allow our observation to glide back toward the terminator line, that twilight boundary, where eternal day transitions into eternal night, we witness an entirely different physical process known as fractional crystallization. Every mineral in the universe has a specific freezing point. Just as liquid water freezes into solid ice at 0 degrees Celsius, liquid rock freezes back into solid stone at specific, much higher temperatures. What is happening now is a spectacular sorting of elements, and one of the prominent compounds found in these oceans is aluminum oxide, a mineral known on Earth as corundum. Corundum has an exceptionally high melting point of about 3,760 degrees Fahrenheit, or 2,070 degrees Celsius. As the eastward winds push the flowing magma into the cooler, 2,000-degree night side, the corundum reaches its freezing point long before the surrounding silicate rock. because of this delicate temperature drop. The aluminum oxide begins to solidify, crystallizing into massive, heavy chunks of solid mineral, while still suspended in the liquid ocean. Here on Earth, pure corundum is the exact base mineral that forms precious gemstones. When laced with trace elements, it becomes vibrant rubies and deep blue sapphires. In the twilight zones of 55 Cancri A, massive, raw formations of ruby and sapphire effectively freeze out of the ocean. Picture ice cubes bobbing gently in a glass of warm water. In a similar way, these giant, solid gemstone formations drift sluggishly through the cooling, deep red waves of liquid silicate, floating peacefully in the eternal dusk. Moving deeper into the planet's anatomy, past the floating crystals and the syrupy waves, we encounter an unusual internal structure. On a typical terrestrial world, there is a clear boundary between the solid outer crust and the molten mantle below, known as the Mohorovičić discontinuity. On the dayside of this exoplanet, however, no solid crust exists. The liquid ocean simply extends downward, deeper and deeper, until the sheer physical pressure of the planetary mass forces the liquid rock to compress into a superheated, solid state. This deep, pressurized layer is likely composed of bridgmanite, an incredibly dense silicate mineral that also happens to be the most abundant mineral, hidden deep inside Earth's own mantle. Imagine holding a large, multi-layered jawbreaker candy, where the outer shell has entirely melted away, exposing the rock-hard, tightly packed core beneath. The ocean simply rests upon this unfathomably hard, pressurized foundation of bridgmanite, creating a seamless transition from fluid wave to solid, unyielding planetary heart. At this very moment, the movement of all this metallic molten material is likely generating another invisible layer of planetary mechanics. When massive volumes of conductive liquid rock and iron flow in continuous convection loops, they act as a vast, natural dynamo. Think of the alternator tucked under the hood of a car, where spinning metallic components generate a steady electrical current to power the battery. On a planetary scale, this flowing liquid generates a profound, invisible magnetic field. This magnetic field arches high above the thick atmosphere, creating a wide protective bubble around the planet. As the host star, Copernicus, steadily radiates streams of charged particles known as stellar wind, the planet's magnetic field catches them. It acts as an invisible silent shield, deflecting the harsh solar energy smoothly around the globe, much like a smooth river stone parting a rush of water. There is a brilliant overarching harmony to all these mechanics. The planet sits comfortably outside the Roche limit, the invisible boundary where a star's gravity becomes so overwhelming it would tear an orbiting body into dust. Janssen remains perfectly balanced just outside this danger zone. It is held safely in place, spinning its heavy, compressed atmosphere, its thick, honey-like waves, and its drifting ruby formations in a perpetual, clockwork orbit. As you take in these magnificent comparisons, the felt-like atmosphere, the oatmeal-like convection, the gemstone ice cubes, allow the flawless, steady physics of this molten world to anchor your thoughts, settling you deeper into a state of quiet, uninterrupted observation. As we continue to observe the heavy, rhythmic motion of Janssen's molten surface, let's pivot our perspective toward the broader cosmic implications of this world. In every planetary system, including our own, is bound by deep, interconnected timelines of growth and evolution. Exoplanet 55 Cancri E, with its surface temperature of 4,300 degrees Fahrenheit, may seem entirely disconnected from the familiar comforts of our daily existence. Yet, The same fundamental rules of chemistry and physics that govern this alien environment are intimately tied to the very elements that shape our own lives. To bridge this immense distance, we can look at the specific chemical fingerprints hidden within the planet's atmosphere. Recent spectroscopy data from the James Webb Space Telescope strongly suggests the presence of carbon monoxide and carbon dioxide in Jansen's dense sky. Both of these molecules are built around the carbon atom. Carbon is widely known as the foundational building block for all known biology. It is the core element forming the structure of every plant, animal, and human being on Earth. Even though the extreme heat of 55 Cancri E prevents the formation of complex biological chains, observing this massive reservoir of carbon gas provides astronomers with a vital, glowing puzzle piece. By studying how carbon behaves under extreme planetary pressures and temperatures, scientists gain a profound understanding of how this essential element is distributed throughout the galaxy, shedding light on the fundamental availability of life's basic ingredients across the cosmos. Another deeply relevant connection lies in the planet's host system. The 55 Cancri system is exceptionally rich in heavy elements. Astronomers measure a star's chemical makeup using a value called metallicity. In astrophysical terms, any element heavier than hydrogen or helium is considered a metal. The star Copernicus boasts a metallicity roughly twice that of our Sun. This abundance of heavy elements in the star's outer layers perfectly mirrors the dense, rocky composition of the planets orbiting it. When you think about the iron in your blood or the calcium in your bones, you are interacting with elements forged in ancient stars and scattered across the universe. The incredible density of Jansen is a direct result of this metal-rich environment, a brilliant demonstration of how a star's unique chemical recipe dictates the exact physical nature of the worlds it creates. Think about how our own understanding of planets has evolved over your lifetime. For much of human history, the 9 and later 8 planets of our solar system were the only confirmed worlds we knew. It wasn't until 1992 that the first exoplanets were officially verified. Today, thanks to relentless observation, the NASA Exoplanet Archive lists over 5,500 confirmed planets beyond our solar system. Jansen was one of the early pioneers in this grand expansion of knowledge, discovered right around the time the concept of super-Earths was just beginning to take shape. This rapid acceleration in discovery is a testament to human ingenuity. The very fact that we can now chart the weather patterns of a magma ocean 41 light-years away speaks to an incredible collective human endeavor to understand our place within the wider galaxy. Let's focus closely on the atmospheric dynamics that make this world so compelling. A key factor driving the thick, eastward winds on Jansen is a process known as the Coriolis effect. Even though the planet is tidally locked to its star, it still rotates on its axis exactly once every 18 hours to maintain that locked position. This rapid rotation generates immense rotational forces. When the superheated gas rises from the dayside ocean, the spinning motion of the planet physically drags the atmosphere along with it, curving the winds. This is exactly how the Coriolis effect operates on Earth, gently bending our trade winds and steering massive oceanic currents. The same physical laws that guide a gentle breeze against your cheek or move a sailboat across the Pacific Ocean are currently whipping vaporized rock across the twilight zone of a distant glowing globe. Now, picture the profound tranquility of the deep time scales at play. The host star, Copernicus, is a stable, mature yellow dwarf, roughly 8 billion years old. Because of its steady, predictable nature, the environment on Jansen has likely maintained its current state for billions of years. Think of the oldest mountains on Earth, or the deepest ocean trenches. They are constantly reshaped by tectonic shifts, erosion, and changing climates. On Janssen, the continuous cycle of melting rock, dense atmospheric winds, and glowing magma waves has been operating smoothly and without interruption since before multicellular life even began to form in Earth's oceans. There is a deep, abiding comfort in recognizing this cosmic permanence, an environment that exists in a perfect, enduring equilibrium. The specific density of this world also offers a fascinating insight into its internal pressure. While the surface gravity is 2.1 times that of Earth, the pressure deep within the planet's mantle is exponentially greater. At depths of several thousand miles, the weight of the 8 Earth mass compresses the silicate rocks so intensely that the atomic structures physically rearrange themselves. This creates layers of ultra-dense minerals that simply cannot exist naturally on the surface of any planet. You can relate this to the process of making a snowball. When you squeeze the loose, fluffy snow tightly in your hands, the pressure forces the ice crystals to bind together, creating a hard, dense sphere. The core of Janssen is a planetary-scale demonstration of this exact process, bound together by unfathomable pressure, creating a silent, locked, and incredibly stable foundation beneath the molten seas. Another spectacular detail, revealed by continuous observation, is the variation in the planet's brightness. When astronomers monitor Janssen, they notice that its infrared emissions are not perfectly static. Instead, the heat signature occasionally fluctuates. Researchers theorize that these variations are caused by massive planetary-scale volcanic activity beneath the magma ocean. This isn't volcanism in the way we picture a mountain erupting on Earth. Rather, imagine a localized area of the ocean floor rapidly superheating, sending a colossal plume of exceptionally hot, fresh magma welling up to the surface. These upwellings temporarily increase the surface temperature of specific regions, causing the planet to shine slightly brighter in infrared light before the thick atmosphere spreads the heat away. It is a slow, a rhythmic pulse of thermal energy, a gentle heartbeat of a living geological system. We can also draw an elegant parallel to the concept of phase transitions, something you experience in your daily life. When you boil a kettle of water, you watch a liquid transform into a gas. When you freeze an ice cube tray, a liquid becomes a solid. The entire environment of Exoplanet 55 Cancri E is a masterclass in extreme phase transitions. On the dayside, the temperature is high enough to boil rock into gas. On the night side, the temperature drops just enough to freeze specific minerals like aluminum oxide back into solid crystals. The planet exists precisely on the razor's edge of these transitions, maintaining a delicate, continuous balance between solid, liquid, and gas. Witnessing this balance allows us to appreciate the delicate parameters of our own existence. Earth resides perfectly within our sun's habitable zone, where temperatures allow water to exist as a liquid, gas, and solid simultaneously. Janssen operates on the exact same principle of balance, merely shifted to the extreme temperatures required to melt stone. The universe operates on a beautiful, scalable continuum, from the gentle evaporation of dew on a morning leaf to the heavy, silica-laden fogs of a super-Earth. The mechanics of nature remain brilliantly consistent, weaving a thread of familiarity through the most alien environments imaginable. Relax deeply into this understanding, knowing that the steady, predictable laws of physics that govern your quiet surroundings are the very same forces guiding the grand, in slow-motion ballet of this distant, glowing world. Let us immerse ourselves in the intricate mechanics of this profound environment by observing the exact science behind the sensory details of Exoplanet 55 Cancri e. One of the most captivating aspects of this world is the precise behavior of light as it interacts with the atmospheric chemistry. The star Copernicus emits a spectrum of light very similar to our Sun, rich in visible wavelengths. However, as this starlight strikes the dayside of Janssen, it encounters an atmosphere heavily laden with carbon monoxide and vaporized silicon dioxide. A fascinating scientific process known as Rayleigh scattering occurs here, the very same optical phenomenon that makes Earth's sky appear blue. But because the molecules in Janssen's atmosphere are much larger and denser, consisting of heavy silicates rather than light nitrogen and oxygen, the atmospheric scattering behaves differently. The heavy gases effectively absorb the shorter blue and green wavelengths, allowing only the longer, warmer wavelengths to pass through. Consequently, if you were to gaze upward through this dense, pressurized fog, the sky would not appear blue or black, but a deep, resonant amber, transitioning into a rich, burnt orange near the horizon. This filtered light bathes the entire dayside in a continuous golden sunset hue, casting long, soft shadows across the rolling swells of liquid stone. The texture of the ocean itself provides a remarkable study in fluid dynamics. While we often imagine magma as a uniform, glowing liquid, the high mineral content of this sea creates distinct textural variations. The predominant minerals, plagioclase feldspar and pyroxene, have different specific gravities. Pyroxene is denser and heavier, while plagioclase is slightly lighter. Under the massive 2.1 g surface gravity, this subtle difference in density causes a physical separation within the upper layers of the ocean. The lighter plagioclase naturally rises to the very top, forming a thin, slightly cooler, and highly reflective skin on the surface of the waves. It is similar to the way a thin layer of cream naturally separates and floats to the top of a bottle of raw milk. This creates a mesmerizing visual effect. The crests of the slow, heaving waves catch the amber starlight, shimmering with a glassy metallic sheen, while the deeper, hotter troughs glow with an intense to opaque white heat. We must also investigate the acoustic properties of this dense atmosphere. Sound travels through physical mediums by vibrating molecules. The denser the medium, the faster and more efficiently sound waves can propagate. On Earth, sound travels through the air at roughly 343 meters per second. In the incredibly dense, high-pressure carbon atmosphere of Janssen, estimated to be up to 100 times thicker than our own, the speed of sound is drastically accelerated. Imagine dropping a heavy stone into a deep pond and watching the ripples travel rapidly outward. Because of this extreme atmospheric density, acoustic vibrations transfer with incredible efficiency. However, the high pressure also naturally dampens high-frequency sounds, absorbing them into the heavy gas. The result is a profound, omnipresent acoustic environment dominated entirely by low-frequency rumbles. The slow, heavy churning of billions of tons of magma generates a continuous, subsonic vibration that hums through the thick air. It is a deep, resonant, baritone drone, a soothing, heavy thrum that you would feel vibrating gently in your chest, just as clearly as you would hear it with your ears. This acoustic environment is further enriched by a specific meteorological phenomenon found near the Terminator line. As we discussed earlier, the eastward moving winds carry vaporized silicates into the cooler night side, where they condense into liquid mineral rain. The science behind this condensation is rooted in a concept called latent heat release. When a gas transitions back into a liquid, it physically releases the thermal energy it absorbed during evaporation. As the molten glass rains down from the dark, heavy clouds, this released heat creates localized, gentle updrafts. These warm updrafts interact with the falling liquid stone, creating a slow, rhythmic convection cycle within the twilight clouds. The physical sound of this mineral rain striking the thick plagioclase skin of the ocean is entirely unique. Because both the rain and the ocean are dense, viscous liquids, there are no sharp, percussive splashes. Instead, it is a heavy, muffled, rhythmic thudding, like the sound of thick droplets of warm wax continuously striking a deep pool of melted candle wax. It is a steady, rhythmic, and incredibly soothing acoustic pattern that plays continuously along the twilight boundary. Deep within the planet's mantle, scientists deduce another incredible process driven by immense pressure, known as solid-state convection. While the outer layers of the planet exist as a liquid magma ocean, the extreme pressure closer to the core forces the silicate minerals into a solid state. However, on geological timescales, even solid rock can flow. The immense heat radiating from the core causes the solid bridgemanite deep within the mantle to become plastic and pliable. Over millions of years, massive columns of solid superheated rock slowly creep upward, carrying internal heat toward the liquid ocean above. Think of the way a glacier of solid ice slowly flows down a mountainside, shaping the valley beneath it. This solid-state convection is the slow, invisible engine driving the thermal dynamics of the entire world. It ensures a steady, uninterrupted supply of heat from the deep interior, maintaining the liquid state of the ocean above through a process that moves mere centimeters per year. As we shift our focus to the chemical composition of the atmosphere, we can explore the fascinating olfactory possibilities of this alien world. While human lungs could never breathe the heavy carbon gases, spectroscopy provides us with a clear understanding of what elements are present. Along with carbon monoxide and vaporized silicates, models suggest the presence of trace amounts of sulfur dioxide outgassed from the deep mantle. If one could safely sample the scent of this atmosphere, the chemistry dictates a highly distinct profile. The presence of vaporized rock and heavy silicates would carry a sharp, dry, metallic scent, deeply reminiscent of the smell produced when a blacksmith strikes a red-hot iron anvil, or the distinct, ozone-rich scent of a high-voltage electrical spark. The trace sulfur dioxide would add a subtle, earthy undertone, similar to the faint scent of struck matches. It is a crisp, heavy, deeply mineralized aroma that perfectly complements the glowing, rocky environment, a sensory reflection of the raw geological power at play. Observe how these elements interconnect. The extreme heat drives the evaporation of the silicates, generating the thick, heavy atmosphere. The incredible gravity compresses this atmosphere, filtering the starlight into an amber glow and accelerating the transmission of the deep subsonic sounds. The eastward winds carry the vaporized minerals to the night side, where latent heat release and condensation create the rhythmic muffled thud of liquid glass rain. Everything is bound together in a seamless, unbroken cycle of cause and effect. Consider the vast silent age of this system. The host star, Copernicus, with its stable, predictable yellow dwarf classification, provides an unwavering source of energy. Unlike younger, volatile stars that frequently erupt with massive solar flares, Copernicus burns with a quiet, ancient maturity. This allows the intricate atmospheric and oceanic systems of Janssen to function with perfect, undisturbed regularity. The sweeping currents of the magma ocean, the slow plastic flow of the solid mantle, and the heavy amber-tinted sky operate in a state of supreme geological equilibrium. Allow your mind to fully absorb the weight and texture of this environment. Visualize the slow, heavy heaving of the opaque white and shimmering plagioclase waves. Listen, in your imagination, to the deep, baritone hum of the molten rock, amplified by the dense carbon atmosphere. Feel the steady, radiating warmth of the dayside, a continuous thermal blanket generated by an ancient star and distributed smoothly by the powerful eastward winds. The mechanics of 55 Cancri E are flawless, a grand continuous demonstration of physical laws operating in perfect harmony across the quiet expanse of space. As you observe this flawless balance, allow the deep rhythmic consistency of this distant glowing world to guide your thoughts into a profound state of peaceful, uninterrupted calm. To fully understand the enduring stability of this planetary system, we must examine the specific, step-by-step processes that unfold gradually over the course of its rapid orbit. Why, observe how the physical properties of exoplanet 55 Cancri E dictate its interaction with the surrounding environment. Astronomers measure a planet's reflectivity using a scale known as albedo. The albedo of Janssen is calculated to be between 0.3 and 0.4 in visible light. This specific measurement means the planet absorbs between 60 to 70% of all the stellar radiation that strikes its surface. Step by step, this incoming light is swallowed by the thick atmosphere and the dark, flowing magma, transforming directly into the deep, radiant heat that powers the global ocean. Watch the careful progression of how this heat is managed deep inside the world. The internal structure of the planet is highly stratified, having settled into distinct layers over billions of years. Scientific models indicate that roughly 30% of the planet's mass is concentrated in a dense, heavy iron core, while the remaining 70% consists of the thick silicate mantle. Because of the planet's extreme proximity to its star, orbiting at a mere distance of 0.01544 astronomical units, a continuous gravitational tug-of-war occurs. This precise distance subjects the planet to immense tidal forces. Phase by phase, as Janssen circles the star every 18 hours, the gravity physically kneads the planet's 70% silicate mantle. This continuous internal friction generates an estimated 10 to the 21st power joules of energy, warming the heavy iron core from the inside out. This geothermal process happens at a steady, unchanging pace, providing a reliable heartbeat of internal energy that slowly pushes magma upward through the solid-state mantle until it reaches the glowing surface. There is a brilliant sequence to how we actually observe this distant world from Earth. Janssen cannot be seen directly with a standard telescope. Instead, astronomers track a process known as a planetary transit. This event unfolds in a highly predictable timeline, lasting exactly 95 minutes. The process begins with a phase called ingress, where the leading edge of the planet's heavy carbon atmosphere just begins to cross the blazing disk of the host star, Copernicus. For the next hour and a half, the planet glides smoothly across the star's face, blocking exactly 0.04% of the star's total light. Finally, during the egress phase, the trailing edge of the planet slips away into the dark background of space. During these crucial 95 minutes, specialized equipment performs a methodical chemical analysis. The James Webb Space Telescope utilizes a specialized tool called MIRI, or the Mid-Infrared Instrument. MIRI systematically measures the specific wavelengths of infrared light passing through the planet's atmosphere, focusing meticulously on the narrow band between 4 to 12 micrometers. It is within this exact step-by-step spectral breakdown that the signatures of carbon monoxide and vaporized rock are carefully decoded, translating invisible thermal radiation into human knowledge. As the planet completes its transit and continues its swift orbit, a subtle atmospheric shedding occurs. The intense radiation from a star with a surface temperature of 5,196 Kelvin slowly boils away the very lightest particles at the top of the planet's atmosphere. Step by step, these escaping particles are pushed backward by the solar wind, creating a highly attenuated exosphere. This results in a faint, invisible tail of sodium and helium gas, trailing directly behind the planet, moving seamlessly through the vacuum of space, like the tail of a massive dark comet. Even the cooling of the magma on the planet's dark hemisphere follows a rigid step-by-step chemical sequence known to geologists as the Bowen's reaction series. As the eastward winds push the glowing liquid rock past the terminator line and into the night, the temperature drops incrementally. With every degree lost, the physical state of the ocean transforms. The viscosity of the liquid stone shifts dramatically from a relatively fluid state of about 100 Pascal seconds to a dense, sluggish, glassy state exceeding 1 trillion Pascal seconds. Within this thickening fluid, specific minerals crystallize in a strict order. Olivine, a heavy iron-magnesium silicate, is the very first to solidify as the thermal energy dissipates. Once the olivine crystals form and slowly sink into the heavy depths, the temperature drops just enough for pyroxene to begin its own crystallization process. This gradual, orderly transition from glowing liquid to settling, solidifying crystals is a masterwork of natural pacing. It is a slow, methodical winding down of molecular energy, a planetary scale demonstration of settling and resting. To truly appreciate the pace of this inner world, we must contrast it with the outer edges of its own solar system. Copernicus hosts 5 known planets in total. While Janssen races through its orbit in 18 hours, the outermost sibling, a massive gas giant named 55 Cancri d, orbits at a distant 5.7 astronomical units. The process of a single year for planet D takes a staggering 5,218 days, or over 14 Earth years, to complete. The entire system is a complex clockwork of varying speeds. The star itself responds to this planetary choreography. As Janssen pulls on Copernicus, the massive star wobbles with a radial velocity of exactly 60 meters per second. Every movement, every wobble, and every orbit is bound by the precise rhythmic laws of celestial mechanics. Moving forward into the final stages of our observation, we can draw a profound parallel between the quiet cooling of this distant world and the natural rhythms of your own physiology. Just as the vaporized silicates cross the twilight boundary to cool and condense, your own body initiates a gradual, step-by-step descent into rest. The thermal energy of your waking hours begins to dissipate. Your core body temperature lowers by a fraction of a degree, signaling to your biological systems that the active day has concluded. Notice how the steady, reliable 18-hour cycle of the exoplanet mirrors the deeply ingrained circadian rhythms guiding your internal clock. There is no need to rush this transition. It happens phase by phase. The slow, rhythmic wobble of the host star at 60 meters per second reflects the gradual slowing of your own resting heart rate. As the heavy olivine and pyroxene crystals settle quietly into the darkening ocean depths, your muscles, bones, and joints settle heavily into the supportive surface beneath you. The planetary mechanics we have observed are ancient, predictable, and flawlessly secure. You can rely on the soothing consistency of these cosmic processes. The heavy carbon atmosphere remains securely wrapped around the world, and similarly, you are wrapped securely in the quiet comfort of your environment. All the complex data, the immense temperatures, and the sweeping geological forces now fade into a soft ambient background hum. The vibrant amber skies and glowing white waves smoothly transition into the deep, cooling cherry red dusk of the night side. As the external world goes entirely still, focus entirely on the slow, rhythmic cadence of your own breathing. Each breath is a gentle wave, rising softly and falling completely. Allow the following thoughts to anchor you in this absolute tranquility, accepting each statement as a fundamental truth of this present moment. My body is entirely at peace. I release all the active energy of the day. My mind is quiet, steady, and calm. I am securely grounded in this space. Every muscle in my back and shoulders is loose and heavy. I am perfectly safe to let go of all conscious effort. My breathing is slow, effortless, and deep. I welcome the natural, cooling descent into sleep. The world around me is quiet and still. I do not need to figure anything out right now. I am entirely supported by the surface beneath me. My thoughts are slowing down, passing gently like distant clouds. I feel a deep, comforting warmth within my chest. There is nothing I need to accomplish. I surrender entirely to the heavy, peaceful rhythm of rest. My mind is a clear, quiet space. I am drifting smoothly into a deep, restorative stillness. Every breath guides me closer to profound relaxation. I am completely relaxed. I am ready for sleep. Good night.